In this short video, I am going to explain what a funnel plot is and why we have them. I am basically using information from this article, What is a Funnel Plot and How to Read Them. It is found at toptipbio.com. But they have great pictures, so I'm going to use them. Here's a picture of a funnel plot. And as you can see, it's a scatter plot used in meta-analyses to visually detect the presence of publication bias. Remember, publication bias can happen because journals tend to not want to publish the negative studies or the no result studies. They want to publish the very emotionally exciting, large, positive studies. So sometimes studies don't get published that have just as interesting results. The results happen to be negative. They happen to be zero, which can be as interesting a result. If the negative or no result studies don't get published, then it looks like on average there's a lot more positive result studies, but that's not actually true. The negative and the no result studies just didn't get published, and that is publication bias. And here's what a typical funnel plot might look like. Each dot is one study in the meta-analysis. So you can see that this particular meta-analysis had 1, 2, 3, 4, 5, 6, 7, 8 studies in it. They combined the data from 8 studies. Now on the x-axis will be the effect size. It could be like here the odds ratio or a log of the odds ratio. It could be a Cohen's d or a Pearson's r or any kind of a risk ratio, anything that will represent the effect size. And as you can see, this line here represents the mean or the average effect size of all the studies put together in the meta-analysis. They put all the studies together, they come up with a mean effect size. Be careful because this line isn't at 0, it's at the mean or average effect size. It'll only be at 0 if there was no effect, but if there's a small effect, like 0.3 or whatever they're measuring it with, it'll be at 0.3. If there's a negative effect, it'll be at negative 0.2 or negative 1. But it's not 0, it's where the average effect size is. For example, if the meta-analysis was about how does aspirin affect knee pain for people who have osteoarthritis, and they had some measure of pain levels, they found that the effect, my coffee just arrived. But back to the aspirin. If the aspirin reduced pain on their pain scale by maybe a full measure from 5 to 4, the effect size would be -1 perhaps. That would be the average effect size. Some studies showed -2 on the pain level, that the pain went down by 2. Some might have shown that the pain went down by 0. Some might have shown it went down by 1 or maybe even that it went up. But the average, when they average all the studies together, the average perhaps was -1 on the pain scale, and so that's where this would be, -1. And on the y-axis is the study size or the study precision. So the larger, the y-axis could be a measure of literally the number of participants in the study, or it might be the standard deviation of the study or the standard error, like this one is, of the study. But the main point is higher on the y-axis are the bigger studies. The bigger studies have more participants, they'll have less error, they'll be more precise. So they'll be up here. For example, in the aspirin versus knee pain studies, the studies with 100 or 200 participants will be up here on the y-axis, and the studies with maybe just 10 participants will be down here. So whether it's a number of participants or standard error, the standard error, of course, would get larger up here with the small studies. So that's why you see these large numbers, 0.5, 0.4, are down here when there's very few participants. So either way, the big studies are up here with lots of participants and low standard error, and down here are the small studies with very few participants and larger standard errors. And here's what a funnel plot will look like if it's ideal, if there's no publication bias. As you can see, these two studies here, the very large ones, are very close to the mean. Why is that? Well, first of all, they're more precise, so they're closer to the actual value of all the experiments put together. Plus, since they're bigger, they were weighted more in the meta-analysis. They had more effect on the mean, just as when you have your final exam versus some tiny weekly quizzes in a course, your final exam contributes more to your course grade, your average, than the little quizzes do. So these are the big final exams. These are the big tests here, the big studies. And down here are the little studies. They're not as precise. They don't come as close to that meta-analysis mean. Some of them will be a little skewed one way, some of them will be skewed another way, and they are less precise, so they're much farther from the mean. But on average, everything averages out to this mean effect size. And here's what an asymmetrical asymmetrical funnel plot would look like. You can see that the large studies are all clustered quite close to the mean because they were the ones that contributed most to the mean. And being larger with more participants, their results will be more precise, more close to the mean of all the studies. And the smaller ones, the slightly smaller ones, are on both sides of the mean. But look at this, all the small studies are showing more of an effect than the mean. Their effect size is greater than the mean. All the small studies have an effect size greater than the mean, and there's no small studies that have an effect size less than the mean, which shows us possibly that there's publication bias here, that all the small studies that had little or no effect didn't get published. And that is how a funnel plot will show you or hint whether there's a publication bias or not. There could be other reasons for the skewed funnel plot. For example, maybe all the small studies in the aspirin knee pain collection use the same type of aspirin or the same brand, and that had a different effect on the patients, or maybe they were all clustered in a nursing home one at a time and there was sort of a placebo effect going on. There could be other reasons, but this is definitely a hint that there might be publication bias in the collection of articles that the meta-analysis found and used in their study, in their meta-analysis. So, in conclusion, when you're looking at the funnel plot of a meta-analysis, remember that each dot represents one study. Along the x-axis is the effect size. This vertical line here is located at the mean effect size, and up high on the y-axis are the large studies, down low on the y-axis are the small studies. If the funnel plot is asymmetrical, there is a possibility that the meta-analysis suffers from publication bias, or the collection of articles suffers from publication bias. You should look into that. And if the funnel plot is symmetric, you are probably okay. There's probably not publication bias within the collection of articles used in the meta-analysis. So I hope you now have a pretty clear understanding of how to look at a funnel plot and what it might mean, and you can go out and have some fun with funnel plots. Bye-bye for now.